Hi there. In this lesson, we're going to be looking at multiplying rational expressions. And really, again, rational expressions are just expressions that are written as fractions. So if we consider these first two examples, when I look at something like this guy, there's two ways that I can approach multiplying these fractions. I could multiply straight across and get a 28 over, let's see, the 12 times the 14. And you'll see right away why this makes this a little bit difficult, 168. And then from here, I have to reduce this thing. And when we look at a 28 over a 168, it might be pretty tough to identify what divides evenly into each. Okay, we might start off taking a guess. Maybe we'll guess something like, I don't know, a 4. Okay, and we'll find out that this reduces to 7 over the 42, and then we can probably see that the 7 over 42 reduces to a 1 over 6. All right, and that's fine. You can do it that way. But remember, there's something else we can do. Whenever we're multiplying fractions, we can always cross-reduce. In other words, we can reduce each of these fractions individually, but we can also look at the numerator here and the denominator here. Okay, and so like the 12 and the 4 can reduce to a 1 and a 3. The 7 and the 14 can reduce to a 1 and a 2. And so when we look at this, it makes it a lot easier now. I've multiplied numerator times the numerator. 1 times 1 is a 1. 2 times 3 is a 6. So I get to the 1/6 much faster by reducing everything that I can first. All right? And keep in mind that you could reduce each fraction individually first as well if you wanted. Like here, I could reduce this to a 2 and a 7, and then I can cross-reduce the 2, and this guy is a 6 and a 1, and then a 1 and a 1. But you see, I get the same thing either way. So remember, anything in a numerator reduces with anything in the denominator when we're talking about multiplication. And it's the same thing with the next one. Again, I can reduce each fraction individually if they reduce. In this case, they don't. So I can reduce any numerator with any denominator. The 9 and the 27 reduce to a 1 and a 3. The 25 and the 10 reduce to, let's see, a 5 and a 2. And now I can multiply straight across. It gives me a 5 over a 6. That's a lot easier than multiplying straight across and then reducing. So keep that in mind. When we multiply fractions, we can always cross-reduce. And it's going to be the same thing here because multiplying rational expressions is just like multiplying fractions. We're going to factor each polynomial completely. So we're going to get all our factors out in the open. And then we're going to reduce. We're going to reduce each fraction individually. We're going to cross-reduce. And then we're going to multiply straight across. And in this step, when you multiply straight across, you can leave that in factored form. Okay? So we don't actually have to multiply it out. We're just going to leave it in factored form for now. And go from there. All right? And for our domain restrictions, we're not going to be looking for those right now. We did a lot with domain restrictions, but just to speed up this process and get us used to multiplying, we're going to forgo the domain restrictions in these particular examples. Okay, so that's your disclaimer for those. So if I look at this first one again, I want to factor everything completely. So like an x plus 5, I can't do anything with. I'm going to leave it as an x plus 5. Underneath here, the 7x minus 21. I can factor a 7 out, which leaves me with an x minus 3. Over here, the 14x, I can't really do anything with. It's a 14 times an x that's already in factored form. And then down here, this denominator, if you need to, take it off to the side. Okay? There's nothing wrong with taking this off to the side and showing your work, building the bridge, coming up with the 5 and the negative 2, and then factoring it using your shortcut. Okay? Some of you are going to prefer taking that off to the side and doing your factors individually, and then coming back and writing these in terms of expressions, rational expressions. Okay? But yeah, feel free to take some work off to the side. Now I reduce. I look at each fraction individually. Nothing happens. So then I cross-reduce. The x plus 5s cancel out. Remember, anything in a numerator with anything in a denominator. The 14 and the 7 can reduce to a 1 and a 2. So now when I look at what I have, again here, this became a 1 because that's what happens when you cancel things out through division. And now I multiply straight across. I have 1 times a 2x, which is a 2x. In the denominator, I have an x minus 3 times an x minus 2. And I'm just going to leave it like that. Okay, I'm going to leave it in its factored form because typically we're going to be finding domain restrictions and that kind of stuff anyway. So leave it in factored form. I get the 2x over the x minus 3, x minus 2. And that's it. If I look at the next one, just like when I'm dealing with regular numbers, if I have a whole number, I can write it as a fraction by just putting it over 1. So I'm going to put this guy over 1. And I'm going to factor everything completely. If I look at the 2m plus 5, I can't factor anything out of there, so I'm just going to leave it the way it is. The denominator, the 3m minus 6, I can factor a 3 out. Leaves me with an m minus 2. Over here, I can build a bridge and factor this one. It's going to be an m plus 3 and an m minus 2. And now I look for any common factors that I can cancel out. I see the m minus 2's are common, so I can cancel those out. Nothing else cancels out, so I'm going to write this in its factored form. I've got in my numerator the 2m plus 5 times the m plus 3. In the denominator, I just have the 3 left, and that's it. I'm going to leave it in this factored form. Nothing else canceled out, so that's my answer. If I look at the next one, again, a 3x squared I can't really do anything with. If you want to think of it this way as a 3x times x in terms of multiplication, in terms of all three of those individual factors, you can. Over here, the x squared minus 4, that is a difference of squares, so I'm going to factor that into an x plus 2 and an x minus 2. The denominator has a greatest common factor of x. So I take the x out. That leaves me with an x plus 3. And here's why I showed that 3x squared as the individual x's, because now I can see that one of these x's is going to cancel out with the one that's in the denominator. I've got a pair of x plus 2's that can cancel out. And so now in my numerator, I've got a 3x times an x minus 2. In the denominator, I just have the x plus 3 left. And that's it. I leave it in that factored form. Okay? Hi there. In this lesson, we're going to be looking at dividing rational expressions. And just like multiplying rational expressions, we treat these things the same way we would treat any type of fraction here. So if I consider these first couple examples, if I'm dividing two fractions when I'm dealing with numbers, remember I would change this. Instead of dividing two fractions, I would change it to multiplying by the reciprocal. So I'm going to change this to multiplying by a 36 over 7. And now it's a multiplication problem. I do the same kind of reducing that I always do. I cross-reduce. The 21 and the 7 reduce to a 3 and a 1. I cross-reduce here. I can reduce this to a 1 and a 3. And now I multiply straight across. That gives me a 9 over 1, which is just 9. Okay? Same thing with this one. Remember, dividing by a fraction is the same as multiplying by the reciprocal. And now from here, I do any kind of reducing that I can. This reduces to a 1 and a 3. This reduces to a 3 and a 1. Even here, the 3 over 3, I can reduce to 1 over 1. And so what happens here, I've got 1 times 1, which is 1. So I get 1 over 1, which is 1. Okay? So when I'm dealing with fractions, just dealing with numbers, I change division to multiplying by the reciprocal. And then I treat it just like any other multiplication problem. When we're dividing rational expressions, we're going to do exactly the same thing. We're going to change division to multiplying by the reciprocal. After we've done that, we essentially have a multiplication problem, which we're going to do the same thing that we did the other day. We're going to factor everything completely. We're going to cross out any common factors, anything with the numerator, with anything in the denominator. And then we're going to multiply straight across. Okay? So really the key step here is to change division to multiplying by the reciprocal. And then from there, it's the same basic steps we've been doing. We factor, we reduce, we multiply straight across. Okay? For example, if I look at something like this guy, my first step is going to be immediately to change this to multiplying by the reciprocal. So this first fraction stays the same. I change the second fraction. Instead of dividing, I'm going to change it to multiplication. And I just flip this second fraction. I change it to multiplying by the reciprocal. And now I do the same things that I've been doing. Okay, so I factor everything completely. The first one, the numerator factors into a b plus 2 squared, which is b plus 2 times b plus 2. In the denominator, I can already see that this is going to have two steps. So if I take that off to the side for a moment, again, it's okay to take work off to the side. I factor out the 2. That leaves me with a b squared minus 4. And b squared minus 4 is a difference of squares. It's a b plus 2 and a b minus 2. So factored completely, I can bring this back over here. That's a b plus 2 and a b minus 2. Over here, the 5b minus 10, I can factor a 5 out of, which leaves me with a b minus 2. And then this just stays as a 4b. And now I cross out any common factors here. I've got a set of b plus 2s I can cancel out. The b minus 2s can cancel out. And now in my numerator, it looks like I'm left with a 5 and a b plus 2. Let me rewrite that. That didn't look very good. In the denominator, I've got a 2 times a 4b, which is just 8b. And that's it. So I change division to multiplying by the reciprocal, and then I do the same basic steps. I factor, I reduce, I multiply straight across. For this one, that first fraction, again, this guy is going to stay the same. And we can think of this as being over 1. I change division to multiplying, and I flip the second fraction. So I multiply by the reciprocal. And now from here, I factor everything completely. Once again, I might take this 6x squared minus 13x plus 6 off to the side. I build my bridge. The two numbers are a negative 9 and a negative 4. This one, you might have to use your factoring by grouping. You split up that negative 13 into a negative 9x and a minus 4x. Everything else tags along for the ride. So we're just using all the factoring knowledge we have. I group the first two together, group the second two together. Out of the first two, I can factor out the 3x, which leaves me with a 2x minus 3. Out of the second two, I can factor out a negative 2, which leaves me with a 2x minus 3 as well. So right away, I can see my two factors of the 2x minus 3 and the 3x minus 2. So taking this back over here, that's a 2x minus 3 and a 3x minus 2. That whole thing is still over 1. Over here, I can factor out. So I factor out that 2. That leaves me with a 2x minus 3. In the denominator, I can also factor out a 2, which leaves me with an x minus 7. And now from here, I start canceling out what I can. In this one, I can see that the 2's cancel. And that's about it. Had I not remembered to change this to multiplying by the reciprocal, I might have accidentally canceled out a little bit more than that. But in this case, that's all that's going to cancel out. So now my numerator, it looks like I have a 2x minus 3. I have 2 of those, so I'll write that as a 2x minus 3 squared. I also have the 3x minus 2. And then in the denominator, it looks like I've got the x minus 7. All right. So in this particular example, not much canceled out. But that's just the way it goes sometimes, okay? We factor it, see what cancels out, and then go from there. And we're going to leave this in factored form. It's far easier to do it that way. If I look at this one, this